All right. So most of you probably have heard about the Hubble Space Telescope for many years. It's actually been operating for over 30 years, 33 years so far, and it is doing all kinds of astronomy. So this little montage shows you examples of everything from studying stars to galaxies to nebulae, and we'll talk a little bit about some of these things. This is a little bit of information about myself. I'm here at the NASA Goddard Space Flight Center. I'm the senior project scientist for Hubble, and that's my email address. We're active. If any of you get into social media, our little address for social media is at NASA Hubble, and you can find out lots about what's going on that way as well. So what and where is Hubble? So Hubble is actually a telescope, but it's put in space to get it above the clouds. So here you see a picture, a photo of the Hubble Space Telescope, and behind it, beneath it, you can see planet Earth. And this is why we put Hubble in space. It's to get it above the clouds and above the blurring effects of our atmosphere. You know, there are a lot of telescopes on the ground, but they have to look through the atmosphere to see deep space. And that atmosphere can even filter out some kinds of light that we want to see, like ultraviolet light. And of course, bad weather days can make it impossible to do astronomy from the ground. But by putting a telescope above the Earth's atmosphere, we get much sharper, clearer views. That was the whole idea behind Hubble. And now there are quite a few telescopes in space taking advantage of being above the Earth's atmosphere. Hubble is not very far away from the Earth, so we don't send Hubble to other planets or to other star systems. We do all the observations from right around planet Earth, and it's just the advantage of being above the clouds that helps us. We transmit commands from the ground up to Hubble to tell it which direction to point. And then after Hubble does some observations, it collects the data and then transmits that data back down to receivers on the ground. So we get that information. On the left here, you see just some info about Hubble when it was launched into space in 1990. And it's only about 340 miles above the surface of the Earth. It's in low Earth orbit, which means it has to move very fast to keep it in orbit so that it won't fall back to the Earth. So it's moving about 17,000 miles an hour, and it goes around the whole Earth once every 95 to 97 minutes. So it does a full orbit of Earth very quickly. And yet, because it has such good components, engineering components like gyroscopes inside, it can point very precisely to a very distant galaxy or star and stay pointed on that object even while it's moving so fast. So Hubble has a really good pointing control system. You'll notice it's about the size, well, you may not be able to guess, but it's about the size of a school bus. And inside this satellite bus is a mirror that's about 2.4 meters across, so a little bit bigger than 2 yards across, that collects the light. And then you see these little antennae outside the telescope. They are there for transmitting data. And then on the sides are the solar panels. So this is what powers Hubble. It's these panels on the side that collect sunlight and recharge Hubble's batteries every time it does an orbit. So that's how we keep Hubble going. Hubble was launched in the space shuttle back in 1990 and put into orbit by a team of astronauts. And astronauts have returned to the Hubble telescope 5 different times after this to do repairs and to upgrade the instruments, to put in new improved science instruments. So that's kept Hubble at really forefront science capability even now. So Hubble is getting the best science now that it ever has because of these upgrades over the years, and also scientists themselves are learning how to use Hubble in very innovative ways. So that keeps the mission very fresh and very strong. And so we've become accustomed to seeing amazing scenes of the universe that we really can't see from the ground, and certainly not with our own bare eyes. So this is a calibration image that was taken using the newest camera on Hubble that was installed in the last space shuttle servicing mission back in 2010. And this new camera sees a wide range of colors, all the visible colors, but also a little bit bluer than blue, which we call ultraviolet light, and a little bit redder than red, which we call infrared light. And here's a picture just showing off that capability of Hubble looking inside a dense cluster of stars. So this is in the middle of what we call a globular cluster. That's a really dense region of stars where the stars are much closer together than our sun is to a neighboring star. So here we have a collection of stars, and because Hubble above the atmosphere can see so sharply, we can differentiate star from star. The light doesn't all blend together. So we can see that there are different colors of stars in this cluster and different brightnesses. If our own sun were in this crowded cluster, it would be like one of the smaller yellowish or greenish dots here. We're not in such a dense cluster, but this really enables us not only to be mesmerized by how beautiful stars can be, but also to do further scientific study. We can take a spectrum of each of these stars, spreading out the light, and that tells us something about the composition of that star. So Hubble's sharp vision enables us to see more clearly, and that enables us to do better scientific analysis of what we're seeing. Yeah, so above Earth's turbulent and filtering atmosphere, Hubble achieves these sharp images. Some of my other favorite regions that Hubble looks at are regions where stars are still forming. So it turns out that our universe is really dynamic, and there's a lot going on, including the formation of new stars. Stars are little balls of gas that have collapsed from within these big interstellar clouds of gas and dust that fill the galaxy. So here, as you're seeing, is an example of a whole cluster of very large stars, stars that are bigger than our sun, that have coalesced and formed out of some of this dense gas within our galaxy. And now that the stars have turned on, stars are just collapsed balls of gas that the pressure gets so high in the middle, they start a reaction called fusion, where hydrogen atoms merge together, and that series of reaction releases light. So stars are showing us that that fusion reaction is going on. And the light from those bright stars goes back to the surrounding leftover gas and can what we call ionize it, which results in it lighting up. So that's why we see these beautiful colors in the leftover gas. And then some winds come off of these stars, these flowing particles come off the surface of these stars, and they can actually blow away some of the leftover gas. But in the intermediate time, they leave behind some of the denser structures, and they protect these long pillars of dust behind them. So if you look closely, like in the lower left, you'll see this pillar-like structure pointing back to the massive stars. That's because the winds from the stars are blowing away the less dense gas, but leaving behind for a little while those denser pillars. And I'll show you some other structures like that. This image is beautiful, and it shows us that our galaxy, our universe, is beautiful and colorful and also active, that stars continue to form. Older stars are also active. So this is a picture of just one star in our galaxy, but it has these kind of cobweb-like shells around it. And that's because this particular type of star, which is called a carbon star, has little hiccups every once in a while where it releases a little bit of its outer atmosphere as it ages. And so after a while, you get these shells of material, and they're full of not only hydrogen, which is most of what composes the star, but also some other elements, and in this case, carbon that's been produced in the star. So these fusion reactions that create the light also produce heavier elements like carbon and iron and oxygen. and then stars can actually release that material and enrich the surrounding gas. So we released this picture around Halloween time recently, last year, I think, because we thought it looked kind of like a cobweb, but it's also quite pretty. And if you look carefully in the background, you see other stars and you see galaxies that are outside of our own galaxy where this foreground star is. So Hubble really allows us to see lots of things, even in the background of images we're interested in. I mentioned that stars are still forming, but we also see stars as they begin to die out, and that's a fantastic process. So here's an example of an older star that's pretty much used up its inner hydrogen that powers that fusion reaction and gives the star the ability to shine light. And as it starts to run out of fuel, it becomes unstable, and part of that instability results in the star expelling its outer atmosphere. So this aging star, which you cannot see, it's buried down in the middle here, but it's expelling its outer atmosphere, in this case, in a kind of bipolar or two-sided process. And it looks kind of like a butterfly. So we call this the butterfly nebula. It's a pretty feature, but it's also very dynamic because that gas moving out is moving out very quickly in the two wings. And that is composed of that material that's been created in the star during its life of fusion. So the helium and the carbon and oxygen and iron are all being expelled out through the wings of this nebula, and they get mixed into the gas so that the next generations of stars that form out of that gas can be enriched by some of this material created in the previous generation of stars. Some stars, as they age, they actually become so unstable that they explode. These tend to be the stars that are much bigger than our sun. So they use up their fuel pretty quickly, and then they become unstable. And not only do they release their outer atmospheres, but they do it in an explosive manner. So what you're seeing here is basically the innards of an old star that ran out of its inner fuel and exploded in what we call a supernova explosion. And this is the debris from that explosion that's still moving out. Now, this explosion happened 1,000 years ago, as far as we could see it from Earth. And there were people in different parts of the planet who actually recorded seeing a sudden brightening of a star in the night sky, in particular from China. They recorded this brightening. They didn't know what it was, but now we know that it was a supernova explosion. And for the last 1,000 years, the debris from that explosion is still moving out. We call it a supernova remnant, and this particular one is called the Crab Nebula because somebody thought it looked kind of crabby. But the different colors here represent the different materials that have been created in that factory, that star, that its fusion processes created sulfur and silicon and oxygen and nitrogen. And those and other elements are mixed into this expelled gas. And Hubble here is picking out the different elements using different filters on the telescope. So we know what's being expelled here. Buried down in here is the remnant dead star. It's called a neutron star, which you can't see very well in this picture, but it's actually a very dense, very fast moving object spinning very fast here. All right, these clouds of gas and dust fill the volume of what we call galaxies. So here's a couple of galaxies. And in this case, the galaxies are actually being pulled together by their mutual gravitational pull. So you see a lot of starlight in the middle of these galaxies where there's so many stars, the light just kind of blends together. And then you see these beautiful spiral arms around the outskirts of the galaxies. These are the regions where often new stars are forming. These nebulae are forming where you get these collapsing balls of gas. And in this case, the two galaxies are being gravitationally pulled together, and eventually they will merge and become one larger galaxy. Here's a couple of galaxies that are farther along in that merging process. It turns out that as we look deep into the universe, we see a lot of cases of galaxies merging together And that's because the gravitational pull of these objects is quite strong if they're close together. So even though the universe as a whole is expanding, these galaxies, if they're close together, can actually be drawn together. And what you're seeing here in this intermediate time before the galaxies fully converge into one is that they are being distorted. Their spiral arms are being disrupted by the mutual gravitational tugs of these two galaxies and the tidal interactions. And these interactions are also stirring up the gas in these galaxies, and that stirs up a lot more star formation. So those bright purple spots you see all around between these and around these galaxies are stirred up star gas clouds that are stirring up more star formation, and that's creating the bright nebulae all along here. So now we know that our universe has always been dynamic, and we recognize now that our own Milky Way galaxy probably is the product of mergers to make it grow in the past. And in a few billion years, we're on track to merge with the Andromeda galaxy, which is our nearest neighbor big spiral. So it's a dynamic place. Fortunately, these mergers don't have a lot of star to star collisions, but they just redistribute the gas and dust into a new configuration and a new shape in the combined galaxy. Okay, so why are we still able to get these pretty pictures and good data from Hubble? It's because we sent astronauts back to the telescope 5 times after it was initially deployed over the last 3 decades to do repairs and enhancements, and that has extended the mission life for a long time. So here's a picture from the last servicing mission where the astronauts have come out of the space shuttle in their spacesuits, and they are repairing some of the electronics on some of the instruments, and they also put in a couple of new science instruments on Hubble. So they left the telescope in very good condition, and so we're enjoying wonderful science from Hubble even now, quite a few years after this mission. Hubble's in good technical condition. Even now, it's at the peak of scientific return. It's a full observatory, so it has several cameras and spectrographs that spread out the light like a prism, so we can get more information about the composition and the motions of the things we're looking at. And the Hubble team and users are forging innovations in the way we use Hubble and how we choose the proposals for which kinds of observations we'll end up doing. And by mitigating some of the degradations that happen over time, you know, the detectors on some cameras and things naturally lose some sensitivity over time. And we figure out ways of working around that so that we can still get excellent data from Hubble. So I'm really pleased with what's going on with the observatory right now. So Hubble is just one observatory. It has a lot of capabilities, but it doesn't have every capability. In fact, we use these different types of observatories, kind of like different musical instruments, to give us different information. Hubble at the top there is an example of a space telescope, and Hubble sees visible light and ultraviolet light and a little bit of infrared light. But we also have space telescopes that's like Chandra that see X-ray light. We have telescopes on the ground that can see different broader fields of view than Hubble can see, and different wavelengths of radiation. So the bottom right there is the ALMA radio telescope array in South America, which sees emission in these radio wavelengths that span what we call millimeter and submillimeter waves. They can see deep into these galaxies where star formation is going on and see deep into these interstellar clouds where Hubble really can't see. The lower left is an example of infrared and visible light telescopes on the ground. These are the Keck telescopes on the top of a dormant volcano in Hawaii. And astronomers are still keenly using some of these professional facilities on the ground, as well as space telescopes, because they all either see some unique band of light, color, and wavelength, or a unique field of view, or they can be used for longer periods of time to do surveys and things that Hubble cannot do. So astronomers typically use a combination of different telescopes and different instruments to do their studies of whatever they're looking at, whether it's galaxies or stars or planets. And we anticipate that will be even more the case in the coming years. Hubble will complement quite a few other telescopes. One of those other telescopes is the Webb Space Telescope, named after James Webb, who was the administrator of NASA back in the Apollo years, back in the 1960s. And so the Webb telescope was launched on Christmas Day in 2021. You can see the picture of the launch there from South America, and the NASA officials there in the lower right watching with both anxiousness and excitement to see if this long-awaited telescope would launch safely and successfully. It took many years to put this observatory together, and thankfully it did launch safely and successfully. So there's an artist's conception of this new Webb Space Telescope. It doesn't look like Hubble. It's bigger. It's got a larger collecting mirror, which you need if you're looking in the infrared wavelengths of light where Webb is peering. So to get a similar resolution or sharpness of view to Hubble in these infrared wavelengths, you need a bigger mirror, a wider mirror. And it's also very sensitive. It can collect a lot of radiation with that big mirror, so it can see very faint things in the distant universe. It's segmented so they could fold it up to fit in the rocket, and then it had to unfold itself in space. And then below it, you see these layers of shields. Those are shielding the telescope from the sun and from the earth to keep it very cold, because since it is designed to see infrared light, that's heat radiation, and we don't want it to be confused by radiation from the earth or the sun. So we keep it shielded and very cold. There's the Webb mirror being assembled where I work in the Goddard Space Flight Center. So that was quite fantastic to be able to look in the window there and see this telescope being put together, the mirror along with its science instruments. Here's a side-by-side of Hubble and Webb. You can see the two different configurations of the telescopes, and they're two different mirror sizes. And they also see different kinds of light, so they complement each other. So here on the bottom, you see kind of swaths of the rainbow of light. You see in the middle what Hubble sees. It sees the visible colors and a little bit bluer than blue, what we call ultraviolet light, and a little bit into the redder than red, which we call infrared light. And then below that, you see the swath of what the Webb, or the James Webb Space Telescope, sees. It sees red light, but also infrared, and much deeper into the infrared part of the spectrum than Hubble can see. So these two telescopes complement each other, because Webb is unable to see most of the visible colors that Hubble does, and Webb cannot see ultraviolet light, which is really important for astronomy. But Hubble cannot see as deep into the infrared part of light spectrum as Webb does. So astronomers are now excited to have both of these facilities. They complement one another, and we learn a lot more about everything we're looking at by having both of them. They're also in different places. And so this little graphic on the bottom is not to scale. If we drew this to exact scale, it would have to extend much bigger than the planet. So it's kind of squished together. But what you should notice is that Hubble is orbiting the Earth in low Earth orbit. It's, it's like I said, about 340 miles above the Earth, whereas the Webb telescope is much farther away. It's more than 1 million miles away, and it's in a place in space we call L2, which is actually orbiting the sun, not orbiting the Earth. So the Webb is orbiting the sun along with the Earth and the moon, and those shields are always between the Webb telescope and the Earth, moon, and sun systems to keep it cold. So that means Webb can be very cold and very sensitive, but it also means we're not able to service it like we did with astronauts for Hubble, because it's too far away. All right, so what are we seeing with Webb? Well, with that infrared light, we can see many things in a whole new light. So here's the edge of one of these interstellar clouds where stars are forming. Massive stars that have already formed off the top of this image are sending their winds and their radiation out, and they are impinging the edge of this surrounding cloud. And from that, you can see these pillar-like structures in that cloud pointing back toward the massive stars as they're being carved out. And scientists are studying within this cloud now the lower mass stars that are still forming. They take longer to form. So this is a beautiful picture of the edge of an interstellar cloud that's being impacted by star formation. Outside of our galaxy, we can see other galaxies. So here's a whole collection of them called Stephan's Quintet. These galaxies appear close to each other, although the one on the left is actually much closer to us than the other four. But the other four you can see are actually interacting. And if you look toward the top three, you can see how they're gravitationally being pulled together and material is being siphoned off from between the galaxies and being shared. It's showing up in that little red path of light below the top galaxy. This is showing up in infrared light because Webb can pick up the heated dust that's being stirred up by the interactions of these galaxies as they are being pulled together and will eventually merge into a much larger galaxy. Do we need Hubble and Webb? Well, absolutely. They see different kinds of light. So here's some news stories that came out a few months after Webb was put into play. And the first one on the top is showing how, I think that was in something called Space Ref, that says that Hubble isn't old news. It's still at its scientific peak. And the lower right article was in the journal Nature, which came out this year, an article about why the Hubble telescope is still in the game, even as the Webb telescope is wowing us. It's because these two telescopes see different kinds of light, and astronomers are very keen to use both of them. I'll show you what that means. So Hubble can see ultraviolet, visible, and a little bit of infrared, what we call near infrared light. So here's a famous picture you may have seen of the Eagle Nebula, where we see these dense columns of gas, again, pointing back to massive stars that have already formed that are off the top of this image, but the winds from those stars are carving out these structures. Hubble can see the visible light, which shows us the reflected light off of these structures and some of the background light in the whole region. But we can't see through the dust that pervades this whole region, and especially in those dense pillars. If we have infrared light, which is what the Webb telescope shows us of the same region, we can see through a lot of that dust. So then we see into these pillars. In this case, the image is rotated a little bit to the right, but you can see those pillars in the Eagle Nebula right there. And you can see a lot more stars in the whole region because the dust does not block the infrared light, so we can see through a lot of it. So here they are side by side and oriented in the same way. The Hubble image on the left in visible light, the Webb image on the right in infrared light. And you can see the difference. We need them both because without Hubble, we wouldn't see the full structure of pillars like this. And without Webb, we wouldn't be able to see deeply into those pillars, seeing more stars. In particular, if you look toward the tops of those pillars, especially on the right, you see some reddish hot spots. Those are where new lower mass baby stars are forming and heating up that surrounding dust. And so we see the evidence of the protostars right there in that infrared emission that the Webb telescope is picking up. Here's that Stephan's Quintet again on the right with Webb and on the left with Hubble. And you can see that they're picking up different features. So we like to have both the visible light image from Hubble and the infrared light image from Webb so that we can see both what the stars are doing with Hubble and what the dust and the heated dust from star formation is doing with Webb. And you can see with the Webb image, you see more of that stuff between the galaxies that's being pulled from one galaxy and siphoned onto its neighbor due to the gravitational interactions. Eventually, those four galaxies on the right will merge together into one. All right, I'm going to try to speed through the rest of this, so we'll have a little time for questions, but we need to get through the solar system and a little bit of galaxies. Here is Jupiter, big giant gas planet, but the luxury of having Hubble operating for decades is that we've been able to look at Jupiter over and over and over again and see if it changes. And indeed, it does change. Jupiter being this giant gas planet, it has these different layers of gas, and the weather actually changes on Jupiter. We've seen that great red spot that you see there on the right. That's a big giant hurricane on Jupiter, and Hubble has observed that storm to be shrinking over time and spinning faster, and new little storms are cropping up. And now with the Webb image, which is on the right, it sees the infrared light from Jupiter, and that's really showing that that great red spot is at a very different temperature from the rest of the planet. And it's also showing us what's interesting on the poles, the magnetic poles of the planet, the aurorae that are creating these hazes that are bright in infrared light. So planetary scientists can use the Hubble and the Webb data to learn much more than with either telescope alone. And here's Webb seeing a different planet, Neptune. And as you see, Neptune also has weather hot spots, and Neptune has rings like Saturn, although much fainter. And yet Webb can pick that up. And Webb is also picking up some of the moons of Neptune. So here you see some of the moons of Neptune being pointed out. And the bright one at the very top there is actually Triton, which is extremely bright in infrared light, which the Webb telescope can pick up. Now, Hubble is the only major telescope, both now or in the foreseeable future, that can pick up ultraviolet light. And so we're keen to keep that capability as long as possible. This is the visible light picture from Hubble of Jupiter. And if we add the ultraviolet light, you see what popped up on the pole. That's the energetic emission coming from charged particles that hit the magnetic field of Jupiter and are channeled toward its magnetic poles. And so you see these energetic light emissions dancing around. Those are, of course, the northern lights, just like we have on planet Earth. But Jupiter has a very powerful magnetic field, and so its aurora is very pronounced. So we look at this with Hubble, and then we use that data to compare with what probes that go directly to Jupiter, like Juno, measure right there at the planet, and we can learn much more about Jupiter's magnetic field. All right. So as we're looking ahead into the future, we believe that Hubble's unique capabilities in visible and ultraviolet light and the sharp imaging we can get above the atmosphere are going to be a powerful complement to other observatories like Webb and other probes and telescopes for all kinds of observations, whether it's looking at our solar system or stars or the planets around stars, which we call exoplanets if they're outside our solar system, or to looking outside our galaxy to other galaxies, to the unseen dark matter that fills galaxies and galaxy clusters, to studying the effects of cosmology and dark energy on the universe as a whole, and even transient phenomena, things that come and go. We'll be using Hubble to look at all of those kinds of phenomena. I'll say a word about the exoplanets. This is a really hot topic. So we didn't know of any planets outside of our solar system when I was in graduate school. But now we know of thousands of other star systems that have planets. And we know by statistics that means that most stars in our galaxy have at least one planet. Now, Hubble is not just discovering these exoplanets. Other telescopes do the discovering, but Hubble pioneered the technique of actually honing in on these exoplanets and studying their atmospheric compositions. This is an artist's conception of a real system discovered by the Kepler telescope of a star with 6 exoplanets in tight orbits. We don't yet have the technology to take a picture that's as detailed as this, so we have to infer the structure of these systems indirectly. And we're designing a new telescope for after Webb that may be able to take this kind of precision picture of these systems. But it's difficult. Right now, we use indirect techniques to find and characterize exoplanets. And I won't describe all of these, but they're like detective techniques of measuring the exoplanet's effect on its parent star. And that gives us some information about most systems. We can take pictures of a few of these systems, but it's difficult. What we can do is study the compositions. And so here on the left is a spectrum of an exoplanet taken with mostly with Hubble on the left. And we miss out on some of the spectral information that we could get if we could see longer wavelengths or redder colors of light. And that's what we see on the right that the Webb picks up. So all you need to take from this graphic is that Hubble can see and detect some types of elements and molecules in exoplanet atmospheres, and Webb can detect other types of molecules like carbon dioxide and water. And together, having both of these kinds of prisms, if you will, to put together to see the full spectrum of light from ultraviolet through visible and into the infrared light that Webb can see, we can start to say a whole lot more about the compositions of atmospheres in these planets that are outside our solar system. What we really want to know is if these planetary systems are similar or different to our own solar system, and we're learning a lot right now on the way. All right, moving outside of our galaxy, here is another galaxy. Isn't it beautiful? Hubble can take gorgeous pictures of these collections of hundreds of billions of stars. We think our own Milky Way looks something like this, but we can't get far enough out to take a picture of it. So we have to kind of infer it from inside. And you can see in the background of this picture some other galaxies as well. Galaxies, as you've seen, sometimes come in clusters, and sometimes these galaxies are interacting with each other, gravitationally dancing around each other, eventually merging. Hubble's famous picture of the ultra deep field shows us thousands of galaxies. These are not individual stars in our own galaxy. These are other galaxies outside our own, and each smudge can contain hundreds of billions of galaxies, of stars, I should say. It's really mind-blowing to imagine how rich our universe is, filled with galaxies. And of course, we're seeing these galaxies as they were in the past, not as they are now, because it's taken lots of time for the light to travel across space to get to us. Some of these galaxies are closer to us than others, so we can compare the more distant ones to the nearby ones and see how galaxies from the distant universe compare to galaxies closer to our own and see if they've changed. And indeed, they have changed. So here's pulling out some of those galaxies from the deep field, and the ones that are closer to us are on the bottom left, and the ones that are farther back in space and time are up at the right. They appear redder because the light is moving through stretching space before it gets to us, and that reddens the light. But those earlier galaxies are a bit smaller. They haven't had as much time to merge with other galaxies too much, and they haven't grown as massive. And their compositions are simpler too, because they have not yet had generations of stars coming and going to produce the heavier elements that we have in our own galaxy and our own solar system. So we depend on generations of stars coming and going to produce heavier elements so that stars in our own epoch of time can have planets and even support life. The Webb telescope can see even deeper because those reddened galaxies, the most distant ones, get reddened farther into the infrared part of the spectrum that Hubble can't even see. So the Webb can see some of the most infant galaxies. And here's one of these deep fields from Webb. Those objects that you see, the big pattern of light arms coming out, that's a diffraction pattern from nearby stars. It has to do with the optics of the telescope. But everything that doesn't have that diffraction pattern is a distant galaxy. And in fact, Webb is showing us that some of the most distant galaxies were actually starting to take on a lot of mass pretty early in the history of the universe. So we think our universe is about 13.8 billion years old. And with Hubble, and now even more so with Webb, we're seeing into that first 0.8 of the 13.8 billion year history of our universe. So we can really see infant galaxies begin to take shape as the universe expanded and cooled. And that's just marvelous to see. Astronomy truly is like a time machine. We even see the effects of dark matter, which we can't see because it's dark, but we know it's there because it creates gravitational effects. And in this case, you see some kind of distorted arcs of light in this cluster of galaxies. That's because most of the mass is in this unseen dark matter between the galaxies, and that's distorting space, as Einstein predicted. And it means that light from background galaxies traveling through this distorted space to our telescope gets stretched out and magnified. That tells us something about the dark matter in the cluster, and it also tells us something about these very distant galaxies that get magnified by this effect. And I'll just mention that there's another telescope being developed that's called Roman. And this picture at the right here shows you that how this new telescope that should launch in about 2027 will have a much bigger field of view. It will see a much bigger swath of the sky than Webb or Hubble. So you see these kind of postage stamp cutouts at the top of this. The Roman telescope will see infrared light like Webb does, but Roman will be able to see a bigger piece of the sky at any one time. So it will be good for surveying how galaxies and stars are distributed across the sky in ways that are much more efficient than Webb or Hubble will be able to do. All right, I'm going to close by saying that I believe Hubble and Webb will continue to inspire all of us in very different ways, scientific ways and other ways. Of course, they give us inspiring science, but we also find that these telescopes actually inspire our whole culture in different ways. And we try to make this accessible to many people. In the upper left, there is a student from the Maryland School for the Blind. And this student is enjoying images from Hubble, where we have put different tactile coatings on the top of these images so that a galaxy feels different than a star feels, and a planet feels different from a comet. And all of these enable people who are visually impaired to be able to enjoy these beautiful, amazing images from Hubble and other telescopes in similar ways that those of us who look at these images with our eyes can enjoy. So that's one way we can serve the world, is by making these discoveries accessible to people so everyone can enjoy and appreciate the universe of which we are a part. Another example is the upper right. That's a stained glass window in a church that's near Johnson Space Center in Texas. And this church has modeled every one of its stained glass windows after Hubble images. So the light can come through the windows and really provide inspiration. I enjoyed visiting that church and taking some of these pictures myself. And then the lower right is a moving van, a U-Haul van that's inspired by Hubble. So there's lots of things, even tattoos. So the public is inspired in many different ways by what we're learning with Hubble and now the Webb Space Telescopes, and all the engineering and dedication that's gone into these facilities that now are inspiring our art, music, of course, science, philosophy, theology, all of the things we do as humans that are enriched by understanding the beauty and the vastness of our universe. And just to be inspired, this is from the space shuttle, the last servicing mission of Hubble, which you see out the window is Hubble. And in the foreground is a model of Galileo's telescope that one of the astronauts took with him on this trip to Hubble. So you could see how Galileo, using his telescope for the first time to take recorded images of space, inspired people to improve the optics and engineering over centuries. So now we have things as sophisticated as Hubble and Webb unveiling the universe in ways that Galileo could never have imagined. This year, we released an image from Hubble that's in honor Hubble's 33rd birthday. It's one of these interstellar clouds in our own galaxy. It's called NGC 1333. We don't have beautiful names for all of these images, but in this case, you see different colors. It's almost patriotic. You see red, white, and blue, but these are features within this interstellar cloud. The top is a bright blue star that's lighting up the surrounding gas. In the middle, you see a swath of dust that's hiding some of the stars that are forming behind it. And in the bottom, you see a little keyhole through this nebula where you can see some of the emission from baby stars that have recently formed in this whole beautiful region of turbulent star formation. So that's our happy 33rd birthday to Hubble image. And I should mention that Hubble is actually a cooperative mission between NASA and the European Space Agency. So we're appreciative of the ESA contributions to this mission over the years. If you want to know more about the Hubble Space Telescope, we have a great website. It's nasa.gov, as in government, nasa.gov/Hubble. Or you can look also in this beautiful gallery of news and images on hubblesite.org, hubblesite.org. And then we're active on social media with the hashtag @NASAHubble. So with that, I want to thank you for your interest in the Hubble Space Telescope and also the Webb Telescope and all we're learning about the universe. And I'm happy to take any questions.